So it's time again. So we're happy to see you all, and let's get started. Today we have Dirk Werner from Berlin, and he's speaking on vector space structure in the set of norm-attaining functionals. Dirk?
Thanks, Benjamin, for the invitation to give a talk in this seminar, this webinar. So let me first try to get the PDF for you. And why doesn't it work now? Ah, okay. All right. Good. So here we are. I'm going to speak on a paper that appeared in spring this year, but had been sitting on the archive for 2 years or so. So it's not exactly very new, and some of you might have heard my co-authors or myself talking about this matter, so apologies in advance. And for the others, let me start by giving the definition of things we are talking about now. And this is something, it's like, aha, okay. I'm doing this right, this is too much. I'm sorry, this is something we didn't try. So how to get to page 1. Fine. And this will be the next one. And this will be the next. Okay, fine. So let's start with the notion of a norm-attaining functional, which is, unless you don't know it anyway, what you have guessed, namely, it's the situation when the functional norm that is by definition a sup of something is actually attained. So it's max. And as you can see from this line, I'm obviously talking about real Banach spaces. So there's no modulus, no real part. And first and most important theorem in this theory is, of course, the James theorem, telling us that every functional is norm attaining if and only if the space is reflexive. So the Hahn-Banach theorem tells us in advance that the set of norm attaining functionals will always be non-empty, and in fact their span will always be weak star dense. And of course a much stronger theorem is due to Bishop and Phelps, and later refined by Bolobash, saying that the norm attaining functionals are actually norm dense. And there is a quantitative version worked out by Bolobash saying if you have a functional and a point where the norm is almost attained, then close to the functional and close to the point, and this is the optimal distance, one can find a norm attaining functional and a support point that follow the definition of norm attainment. So let's look at some examples. If the space is the space C0 with a sup norm, then all sequences of finite support are norm attaining and the others aren't. For the corresponding space of summable sequences, the norm attaining functionals are those that are represented by bounded sequences that peak at some point. So the sup norm of Z is attained at some coordinate n. And for the topic of this talk, let us note that, of course, on C0, the norm attaining functionals, they form a linear space, but on L1 they don't, because it's easy to cook up examples of two norm attaining functionals on L1 whose sum is not norm attaining. However, in this latter case, there's, of course, a subspace, a sub-vector space to be precise, consisting entirely of norm attaining functionals. And since little L1 is a dual, this is clear that the pre-dual C0 will be a closed subspace of norm attaining functionals. But you could do a little bit because there's also a dense subspace that works. For future reference, let's note that the span of the norm attaining functionals on little L1 will be the whole dual. We will consider this condition later again. So here are the corresponding examples in the case of function spaces. For the space of continuous functions, you can characterize the measures that give rise to norm-attaining functionals by this condition, that the supports are separated, as it were. And for the function space capital L1 on 0, 1 or any old other measure, it's again those L infinity functions that peak, meaning that they attain the sup norm, the essential sup norm on a set of positive measure. Again, we see that in these examples, there are infinite dimensional subspaces consisting entirely of norm-attaining functionals. And as far as capital L1 is concerned, again, the span of the norm-attaining functionals is the whole dual. So I'm going to talk about whether these examples are representative of the general situation or whether things are more complicated. And the modern lingo to express this is the notion of lineability. So a subset is called lineable if it contains an infinite dimensional subspace. Maybe you have to add the 0 because otherwise it's impossible. And it's called n-lineable if it at least contains an n-dimensional subspace. And the first and maybe most interesting examples of this kind was given by Gurari in the 60s, who proved that the nowhere differentiable functions are lineable in the continuous functions. And of course, here one has to add the 0 to S to make this work. So later it was proved that there's even a closed linear subspace consisting of nowhere differentiable functions and isomorphic to little L1. This was proved by Gurari, Fonf, and Michail Kaditz. And in fact, it was proved that every separable Banach space can occur as a subspace of this example. So the question I'm addressing now is the lineability of the set of norm-attaining functionals. And this was asked explicitly by Gilles Godefroy around 2001. And he asked, is it true that the norm-attaining functionals always contain an infinite dimensional subspace, as in the examples I've just told you? And one can even ask a more modest question by asking for a subspace of dimension 2. Since there was no progress in the first 10 years after Gilles asked this question, this was a question that was likewise unanswered. Of course, we don't have to ask about dimension 1 because there always are such functionals. So the previous slide gave you examples where G infinity holds, and depending on what you call a classical space, you can say that in all classical spaces this is true, and more recently it was proved that it's indeed always true up to renorming. So one can renorm every space in such a way that there's a linear subspace of norm-attaining functionals with respect to the new norm. Now, in general, this problem was considered and answered. I'll show you how in a minute. And one has to make a little detour to find the answer. And this goes through the notion of proximality, which means that the quotient norm of x mod y is attained as given in this formula here. So what is the connection to norm attainment? It's this simple lemma: the functional is norm attaining if and only if the kernel is proximal. In the 70s, Ivan Singer published a small booklet on abstract approximation theory, and there he asked whether it is always true that there is a proximal subspace of codimension 2. The line above tells you that there's always a subspace of codimension 1, namely the kernel of a norm-attaining functional. So the connection between the problems G on the previous slide and this one are given in this implication. So if you have a proximal subspace of finite codimension, then the annihilator is a finite dimensional subspace consisting entirely of norm-attaining functionals. So if the answer to Singer's problem is yes, then the answer to the problem G by Gilles Godefroy is also yes. And as you can guess, things are not so easy because Charles Reid proved that there is a counterexample to Singer's conjecture or Singer's problem. That is to say, there is a Banach space such that no subspace of codimension 2 is proximal in the space X. I'll explain the construction in a minute, but for the moment, let us just dwell upon this theorem, this paper a little. So as you know, Charles Reid passed away unexpectedly in 2015, and one of his hobbies was solo cave diving, as you can see on the photograph on the right, which is taken from his homepage, which at least is still alive. And this paper containing the solution to Singer's problem was written in 2013 and uploaded to the archive, but it wasn't published during his lifetime. So it was submitted to the Israel Journal, but then Charles passed away and someone else had to take over to make the corrections and implement the suggestions by the referee. So it took more than 3 years after his death before this paper got officially published in the Israel Journal. But it was available since 2013, which helped other mathematicians to work on that. And one of them is Martin Mutil from Prague. So remember that a positive solution to S would give a positive solution to G, but we have a counterexample to S. So therefore, this might or might not be a counterexample to G, to G. And Martin worked on that, and he proved the following results. Remember that for a finite codimensional proximal space, the annihilator consists of norm-attaining functionals. But the converse is not true in general. However, if the quotient space X mod Y is strictly convex, then this converse is true. Concerning the space constructed by Reid, Martin proved that this condition is indeed true. So in conclusion, the space constructed by Reid is in fact also a counterexample to Godefroy's problem. So this problem was solved at this moment, and the proof that Martin Mutil gave was a little bit complicated, and my co-authors made a simpler version of that proof. In particular, they showed that the second dual of that space is strictly convex, and therefore not only the two or finite dimensional quotients are strictly convex, indeed all the quotients are strictly convex. Now let me lead you through some steps in the construction of Charles Reid's space. And what he did was an extremely clever renorming of C0. And some of the ingredients are as follows. So first of all, you take this set omega consisting of sequences of finite support having rational entries. So this is a countable subset of functionals, as it were. And then you enumerate this countable set in such a way that every element appears infinitely often. Then you go on to take a sequence of integers that increases sufficiently fast. So here are the conditions that Charles needed. And then you renorm the space in the following way. You take the original norm and you have this sum as a perturbation, and the factor 2 to the minus something is of course meant to make this series convergent. So this is the norm. You can write it down fairly easily, but what is not easy at all is to show that it has the properties that you expect. So Charles Reid showed that this renorming fails the condition S, and Martin Rutil, relying on that, showed that it even fails the condition G. So the space is quite aptly called XR because both Reid and Rutil's names start with the letter R, and we stick to that. So here's a detail that I will comment on later again. These UNs are members of the set omega, and the set omega is exactly the set up to this condition of the rationals is the set of norm-attaining functionals on C0. So these elements here consist of norm-attaining functionals on C0 for the original norm. So this is worth keeping in mind. So this is the point where the actual talk starts, because I want to report on this paper I was mentioning, where we try to approach problem G directly without doing the detour to first study problem S. And so this is what we want to do. And we will look at Banach spaces X that can be renormed to fail this property G. And we use a very simple-minded renorming, namely you can again take the original norm and perturb it by some sum, and this can be thought of as an operator into little l1 that has this form. And as I said, this is practically the same type of norm that Charles Reid was using, and never mind this factor 2 to the minus n. This is inessential. It could be 3 to the minus n as well. The main purpose here is to make it a convergent series. So here's our ansatz, how to proceed. And of course, the main point is to choose these functionals Vn star. So the Vn star are at our discretion, and we'll try to choose them judiciously so that we can indeed show that the norm-attaining functionals do not contain two-dimensional subspaces. So what can be said here? Let's just try to calculate and see how far we come. So certainly at some point we have to make additional assumptions, because for a reflexive space this will never work. It is always a subspace. Here is our renorming with the Vn star arbitrary for the moment. Then the first observation is that the dual ball can be characterized as this Minkowski sum consisting of the original dual ball and the sum of these segments. Now taking norm-attaining functionals for the new norm. So this NA1 indicates that I'm now looking at functionals of norm 1. So what can we say? We can decompose it according to the first line. But if X star is norm-attaining for the renorming, then, and the support point should be X, then this X naught star will also be norm-attaining with the support point X. And also, whenever Vn star of X is positive, then our choice of Tn must be 1. And when it's negative, our choice of Tn must be -1, because otherwise this won't be norm-attaining to begin with. If Vn star of X is 0, we can't say anything, of course. So this is the decomposition that we get for a norm-attaining functional. Now let's take a second one, and after that, look at the sum of the two. So here we have a second norm-attaining functional of norm 1. We write down its decomposition, and we go on to look at the sum. And our ultimate goal is to show that this sum is not norm-attaining. And as I said, we must have additional assumptions on the way, because for a reflexive space, we'll never be able to prove that. Good. So we assume that this sum is norm-attaining. So then we can normalize it. This is the Z star that you're seeing. And we can decompose Z star in the above fashion, and it has a support point that will only be implicitly used in the next calculation. So we got that. So since if lambda is the norm of the sum, lambda z star is exactly x star plus y star, we get that this sum is equal to 0. On the other hand, if we plug in the right-hand sides, we end up with this item. So let's continue. Here's where we ended up. So now we wish to draw conclusions from that. And first of all, we have two brackets that are whose sum is 0. And the first thing we wish to conclude from that is that both brackets are 0. So for this, the Vn star have to be sort of orthogonal to the left bracket. So the left bracket is by assumption the sum of norm-attaining functionals. Therefore, it's the span of the norm-attaining functionals. So our first wish is that we should select the Vn star in such a manner that they are, in a way, orthogonal, whatever that means, to the span of norm-attaining functionals. And at that point, I remind you that the Vn stars that Charles Reid was choosing were norm-attaining functionals themselves. So this is the decisive juncture where the two approaches differ. Fine, so we are cooking up a wish list, and let's see whether we can make the wishes come true. This was our first wish. Now the second wish is, if the second bracket is 0, then we want to know that the coefficients are actually 0. So therefore, we would like to have some, let's say, Schauder basis character of the Vn star so that we can make a conclusion like that. This is the second wish. And now for two wishes, we had two support points, one belonging to x naught star, one belonging to y naught star, and we can't conclude that they are distinct. They might be the same, but let's wish that we are in the lucky situation where they actually are distinct. So then one can separate them by the Hahn-Banach separation theorem, but we wish to separate them by means of the functionals Vn star. And we wish to separate them in such a way that one value is negative, one value is positive. That is in terms of the Tn here, one is +1, one is -1, and therefore the sum is 0. So this should happen for many n, say, whatever this may mean. And on the other hand, we would still like to conclude that the Sn appearing here has to be non-zero at least once. So the conclusion of that would be, we have n's where this sum is 0, but this is not 0. So the whole item here is non-zero, but in wish 2, we arranged it in such a way that the sum is 0. So when this program works, we have a contradiction. When this program works, we have a contradiction, and this means that our assumption that the sum x star plus y star is norm-attaining is refuted. So usually you have only 3 wishes, and here I had 4, but actually the third wish is of minor importance, and we can get away with it very easily, as I will show you in a minute. Now, to implement this wish list, we made a definition of what is called a modest subspace. For that, I have first to recall the notion of an operator range. So you take a bounded linear operator from some v to some w, then its range is a very specific subspace of w. It's called an operator range. And here is the key definition. We take a space w and a subspace z. This is called modest if it is sort of next to an operator range. So if there is an operator range that misses z, the intersection is 0. It's like two orthogonal subspaces. And there's a version for dual spaces. If this W is a dual space, then we can talk about weak star topology. And then we call Z weak star modest if it is next to a weak star dense operator range. Incidentally, these operator ranges here must be separable. So this is part of the definition. Right. First comment here is, once we have such an operator range Y, it will sometimes be advantageous to replace it by another one. And it will be advantageous for us to replace it by an operator range coming from an operator defined on little l1 rather than V. And this can be done by means of this implication here, which depends on Markushevich bases. And I think the first person to observe this was Michał Ostrowski. Right, here's the key example now. The space of sequences of finite support considered as a subspace of the dual of C0 is modest. So what do we have to produce? We have to produce an operator range that is disjoint from this subspace. And here's a way to do it. You take an operator defined on the disk algebra that evaluates a function in the disk algebra at the points 2 to the minus n, multiply by 2 to the minus n to get a convergent series. And this is the operator range that we were looking for. To see that indeed the range does not intersect C00, this is simply the theorem in complex analysis. If you have a function, an analytic function with infinitely many zeros inside the ball here with the limit point 0, then this function must be 0. And you can also prove that it's dense. So here's the main theorem now. If the span of the norm-attaining functionals is a subspace that is weak star modest, so it sits next to an operator range, then when we have a renorming that fails the Godefroy condition and consequently fails the Singer condition. And it is with this condition that the outline about the wish list really works. So okay, this renorming will be called a read norm, fine. Let's look at the ansatz and let's look out at our wish list and let's see what we can do. So we started from renorming X by means of this P, and we want to choose the Vn star, the functionals in a proper way. So the key technical lemma for all this is that by modesty, we have this operator range, but we want to replace the operator range by a sort of nicer operator range, namely one where the operator is defined on little l1, which is technically easier because it's easy to define operators in little l1. And whenever you look at the image of the unit vector basis, this is this sort of the Vn stars, then the normalized images are dense in the unit sphere of the operator range. So first of all, by this modesty assumption, there is such an operator range, and by the lemma, there's a better operator range. And with these Vn stars, we will work now. So first of all, the Vn stars come from the operator range, and the operator range was disjoint from the span of the norm-attaining functionals, and this was more or less what we were wishing in wish number 1. Then in wish number 2, we were going to conclude that the coefficients in the sum are 0 once the sum itself is 0. And this is so now the Vn stars are not a Schauder basis, but they are the image of a Schauder basis. So therefore we can conclude this after all. And now for wish number 4, which was the wish that we can separate the different support points by means of many Vn stars. This follows from the density that we have here. And the fact that still the coefficients that pertain to the sum are not always 0, this is a matter of norm attainment. So I haven't talked about wish number 3, which says that we wish that the two support points are actually different. And this is something we cannot have in general, but if x and y are the same, then we simply change horses. Instead of looking at x star plus y star, we look at x star minus y star, and the support point now would be minus y. And if x equals y, it certainly does not equal minus y. So this can be overcome very easily. Good, so this very quick summary of the steps in the proof will show that for Banach spaces satisfying the condition of the theorem, there is such a renorming. And I think this will come up next. Yeah, so this is again the summary. If we do all this, then we see that whatever x star and y star we pick, if they are linearly independent, I think I didn't mention this from the beginning, if they are linearly independent, then either x star plus y star cannot be norm attaining, or x star minus y star cannot be norm attaining, maybe both. Right, so which spaces now satisfy the assumption? For which is it so that this span has this modesty property? And the first example is C0, because in our example, we pointed out that C00, the norm attaining functionals that form a subspace themselves at this point, they are modest. So we recover now the results of Reed and Mutil by this new approach. But there's a much wider class that we can cover now, namely separable spaces containing a copy of C0. They can also be renormed in such a way that the Godefroy condition doesn't work. And here's a quick proof for that. So since the space is separable, the copy of C0 we are considering has to be complemented. And we first renorm X in such a way that the direct sum is the infinity direct sum, and the norm on C0 is the traditional subnorm. So we start from this renorming. And then one can show that the norm attaining functionals for this renorming have to be weak star modest. So our renorming for the Reed norm is actually a renorming of the original norm. So C01 is one example of that. And here are some comments concerning geometric properties of the norms we are considering. So actually, the norm I've described is always strictly convex. So, and the dependence of epsilon will show up in a minute. So let me do this first. So for each epsilon, there's such a norm that is strictly convex, and the dual is strictly convex. So the norm itself is smooth, and the dual norm is rough. And rough means that slices are big. Every slice has almost diameter 2. And an additional benefit for spaces with a separable dual is that the second dual will be strictly convex as well. So not only are there norms as described in the main theorem, there are also geometrically nice norms that do that. So extensions and questions. Here's an extension of the theorem. So until now, we have only looked at separable spaces, and this theorem will also cover L infinity. So a Banach space containing a copy of C0, we can't get away with that. That allows a countable system of norming functionals. It's not one norming, it's norming in the sense that you can read here. This also admits a Reed norm. And some steps in the proof here are as follows. First of all, such a space is a subspace of little L infinity, almost by definition. And then we are using the Lindenstrauss-Rosenthal theorem that Przemek mentioned the other day to map the subspace isomorphic to C0 to the actual real C0 in L infinity. And then it is not true that C0 is complemented because the original space might still be L infinity, but it's an M-ideal, and the geometric properties of M-ideals, they help coming around this difficulty. So this is probably the widest class that we know of where such read norms exist. And let me comment that this theorem covers certain non-separable spaces, but there's a limit to that. So very, very non-separable spaces can be proved to not admit read norms. So for example, if you look at little L infinity over an an uncountable set, then however you renorm this space, it was proved by Partington that the renormed version of that space contains a copy of the subnormed L infinity over the naturals. And since this is one complemented, you can easily check that there's always a linear subspace of norm-attaining functionals. So the theorem itself will not be true for all Banach spaces. This much is known, but it is not really true and known whether it's true for all separable spaces. For instance, about little L1 and capital L1, our approach doesn't say anything. And for little L1, it's even worse, because at the very beginning, we discussed that for little L1 with its original norm, the span of the norm-attaining functionals will be the whole dual, and likewise for capital L1. But Bourgain proved that for every space with a Radon-Nikodym property like little L1, it is so that the span of the norm-attaining functionals will be the whole dual. So whatever renorming of little L1 we start with, our approach will not work because we are looking for something that is beyond the span of norm-attaining functionals. And in little L1, there's no such thing. And for capital L1, for the original norm, there's no such thing either, but I don't know about renormings, whether you can renorm little L1, capital L1 in such a way that the span of the norm-attaining functionals will not be everything. So this is open. And another question that Richard Aaron once asked. So we now know that there are spaces without two-dimensional subspaces in NIX, but is it possible that they have two-dimensional subspaces, but not three-dimensional subspaces? And this was answered by Miguel Martin, who showed, as for this specific question, that the direct sum of two spaces of read type will work direct sum by means of an LP norm, like L2 norm. And in general, his answer is there's always, given n, there's always a Banach space where the norm-attaining functionals contain n-dimensional subspaces, but not n+1 dimensional ones. Okay, so I think this is pretty much what I wanted to say. Thanks very much.
Oh, thank you, Dirk. Questions and comments?
Couple of small questions, Benjamin.
Yeah, go ahead.
Yeah, Dirk, how about James space, about, I mean, the lineability of its norm-attaining function?
For the James space.
Right.
So the original, I mean, the James space that is isometric to the second dual
Exactly.
will certainly have such a subspace because it's a dual space. Every dual space, the pre-dual will be a subspace consisting of norm-attaining functionals.
Okay. All right. And how about this property for the Lipschitz dual of a Banach space?
I don't know, but maybe someone in the audience knows more about this. Thinking of Vova, do you know anything about this?
All right. First, the Lipschitz dual contains the original dual. So if there is a norm without norm attaining, without two-dimensional subspaces, a norm attaining linear functional, the same renomen works for Lipschitz dual. But I don't know, never was thinking and cannot answer at once what happens in the case if we don't have a read norm in the original sense, whether it, if we if we don't have a read norm in original sense, this means that the dual is a subspace, and then Lipschitz dual also has a subspace because it's bigger.
Okay.
So in one direction there is implication, but I don't know what happens with implication in the
Right,
other.
right, right. Yeah, it's more non-trivial, right?
I have a question, maybe. I'm sorry, my camera is not working, so I cannot be shown, but I hope I can be heard. Thank you, Dirk, for this nice lecture.
Thank you, Gilles.
I had one more question about linearity in norm-attaining functionals. Maybe you know about this. If you take a dual space, isometrically a dual space, so that's a set of norm-attaining functionals, so I call it X star. X star such that the set of norm-attaining functionals is a vector space. Is this forcing reflexivity of X? What I can show is that X is necessarily weakly sequentially complete. But I don't know if X is necessarily reflexive. Do you have any feeling about this? Or?
Not really, but just to make sure that I understand the question correctly, you are looking at a space like C0, where the norm-attaining functionals are an actual vector space, but you want this to start from a dual space.
Yes, if for C0 it works, as you said, for little L1 it doesn't. But if you have a dual space, an isometric dual space, which has, say, the C0 property, if you call it this way, is it forcing reflexivity? It's plausible, but I cannot show it. Any information about this is, of course, welcome. Last thing again, since I don't want to spend too much time, but what I can show if I call that space X star is that the predual X or any predual X is weakly sequentially complete, which is falling short for showing reflexivity, but this is a step in this direction. So thank you, Dirk, and best regards to everyone.
Thanks.
Thank you. Any other comments?
Thank you for your question, Jim.
Okay, thank you so much, Dirk, again. That was a wonderful talk. Let me stop recording, but we can continue our conversation after that.